Thank you very much. It's my pleasure to give the talk here on sensing with Wi-Fi, theory, practice, challenges, and limits. Before I start the talk, I'd like to express my full appreciation and also the acknowledgement to the great efforts and hard work from my PhD students and research fellows who have significantly contributed to the research that I'm going to talk about later. So with that, let me move on to the talk. So Wi-Fi sensing is actually belongs to the category of radio frequency sensing. Also, we call it RF sensing. The rationale behind the RF sensing is very simple, that we transmit the wireless signal, and we detect the signal reflected from the environment, right? Like what is shown here, from the object, moving object, human beings, etc. And by detecting the reflected signal, we are able to sort of get information about the environment. And by that, we can detect any dynamics from the environment, and infer any activities going on in the environment. And Wi-Fi sensing has been used for many applications, including human tracking, human-computer interface, vital signal monitoring, health caring, security system, etc., etc. Right. A specific nice feature about Wi-Fi sensing is that it's contactless, right? So people doesn't have to wear any device, and there is no dedicated sensor, and the sort of the coverage of the sensing is very wide. Specifically, it can actually be used for detecting non-cooperative object, right? Doesn't like in a typical wearable environment, you need the subject that you want to sense about to wear sort of devices. Okay. Using Wi-Fi sensing, we can detect any non-cooperative object as well, like in the security applications, right? Having said that, it seems a little bit odd, right? And talking about the nice features of no need of wearing anything in the WiFi's workshop, right? But I do believe that the Wi-Fi sensing, or more broadly speaking, wireless sensing is complementary to wearable systems. In terms of the flexibility of the system deployment, and I do believe integrating the two types of system will actually envision more application, and also ease the future development of systems for more applications. Right? Okay, so let me give you one example. Actually, this is one system that we have recently been studied in NTU. Right, this is we are using the Wi-Fi for detecting human activities, right, in the room. And you can see that this is in the NTU open house testbed, where we have a room and we are using the Wi-Fi signal for detecting the human being inside the room. And you can see that from the camera view, right? We know that, okay, how this person is moving, but we're not using any information from the camera. And we are solely based on Wi-Fi, and we can detect whether it is moving or standing still. And more importantly, we are trying to catch this sort of critical fall of human being. And you can see that after we detect the falling, and we will be able to trigger alarm. And this is particularly important for healthcare, especially for the aged groups. And there have been a lot of other applications proposed recently in the research community, including like the work from MIT in detecting moving objects beyond the walls, and the work from Washington in recognizing the activities of human beings and also the gestures by Wi-Fi signal, detecting of the human breathing and heart rate by Wi-Fi, even the emotion recognition using Wi-Fi, right? And the sleep quality monitoring and the human posture estimation, right, based on solely Wi-Fi signal. And recently, there have been a lot of startup, commercialization efforts that tries to bring this technology to more productization, right, in industry. And you can see many emerging startup companies trying to build system around Wi-Fi for motion detection, activity recognition, critical health status monitoring for human beings, etc. Right. So I guess here a very basic question, especially for the community in WiFi, right? Especially for those who haven't done research in this area, maybe a very fundamental question is, okay, why Wi-Fi sensing is possible, right? What is the magic behind it? Let me start with a very simple example, right? Where you have a transceiver, right? That is your mobile device that tries to transmit through Wi-Fi to the AP, right? Like what we show here, and we have an environment where we have obstacles, we have moving objects, human beings around. What happens is the transmitted signal doesn't just go straight to the Wi-Fi AP, but actually propagates through different paths, which might be direct line of sight paths or other paths reflected by the surroundings, okay, like shown in this figure, right? There are, I mean, let's make it very simple. Suppose there are only 4 different paths, and then what you get is really the superimposed signal. That's a signal from different paths adding together, right? Here, okay. And suppose we are sending some modulated signal, then what we are getting here is an add of different copies of this modulated signal here, right? If your modulated signal is complex itself, then the superimposed signal is also very complicated. But let's make it very simple. Suppose we are transmitting a very simple signal that's a single tone, right, of a frequency f, okay? And let's use a basic trigonometric expression, and we can use a more complicated, I mean, complex exponential for math works, but here let's make it very simple. Suppose we have a very simple frequency f signal transmitted from the mobile device. And what happens here is when the signal propagates through different paths, it may attenuate, and also because of the transmission distance shifted in time with different effect, okay? So from the first pass, it may be attenuated by alpha 1 and then shifted by theta 1. And for the second pass, it's attenuated differently and time shifted differently. And then at the end, where is the receiver, when they add up together, what do we get? If you haven't forgotten what you have learned in signal and systems, then a very simple answer is yes, you get basically the signal of the same frequency, right? That is also 2 pi ft, but with a different attenuation factor and a different shift. Okay, that is a super imposed signal of the same frequency components from different paths. Okay, what you get actually can be parameterized by the attenuation and its time shift. Okay, then suppose we are transmit signal with a bandwidth here, right? Now we have multiple frequency components. Then what you can get here is multiple different parameters for this attenuation of that frequency component and time shift. And it's different across different frequencies because different frequency signal has different wavelengths, and the same propagation distance may result in different attenuation and time shift. Okay, that's the basics. And then, but from this example, right, you can see very clearly that the superimposed signal can be parameterized, and the parameters about those different frequency components do tell you something about the environment, because different environment has different multipath profile. Okay, those different paths may be different, and as a result, you may have different parameters at the receiver side. Okay, and then reversely, using those parameters, it gives us opportunity to recover sort of information about the environment, and that is the basics of this Wi-Fi sensing. Okay, then you can imagine an environment where you have some objects moving. For example, in this case, this person is moving around in this room, and the particular propagation path related to that person is varying across time, right? And as a result, what you get at the receiver side, the parameter about the channels will vary as well. And if we can sort of associate those parameter variation to the moving objects, then we can sort of recover what is the dynamics of the environment. And by that, we can sense sort of different activities from the human being. Okay. this idea actually has been practiced for many years. Okay, 20 years ago, right? People have been using this idea for radio frequency localization. Okay, the basic idea is, okay, now the environment, let's suppose the environment is not changing or not changing very fast. Instead, the transmitter is moving around and we want to sort of locate the transmitter itself. Then what happens is the movement of the transmitter will also result in the dynamics of those propagation paths. And as a result, if we look at them as a whole, we see attenuation of the signal. Okay, the signal strength received at the receiver side may vary. And particularly, we can see, statistically increased signal strength when the transmitter moves towards the receiver and decreased signal strength when the transmitter moves away. Okay, that is a basic idea. And that is a very rough utilization of this idea. And that has been done 20 years ago in many systems, like the radar system, which is built 20 years ago by Microsoft for using Wi-Fi for locating the transmitter. Okay. And the landmark, which was built for locating the RFID tags, okay, by looking at the signal strengths. And as you can see in those examples, right, they were pioneer applications at that time, 20 years ago, but they were making use of the RF in a very rough way, right? They are looking at the combined signal strengths, not a detailed components of different signal propagation paths. And that is also limited. That was also limited at that time by the hardware that we had. Okay. And most recently, actually, we have seen that the Wi-Fi standards, recent standards like 802.11n, AC, or the rolling out AX, they require so-called channel state information, okay, for transmission purpose. And then what is a CSI? Basically, that is associated with the modulation scheme, right? We are moving from modulating the whole signal within the band to cut the band into small pieces and modulating signals separately in those we call subcarriers. And as a result, we need to have those channel coefficients for different subcarriers, and we call them CSI. Okay, and the CSI was proposed and used for communication purpose, but we see it as a very detailed and informative way for us to learn the environment dynamics. Okay, compared with what we did 20 years ago using signal strings, using CSI is more like, okay, we have a more detailed and specific view of how different frequency components are affected by the channel. And by looking at those different frequency components in a combined way, we can sort of recover as much as possible details about the environment. Okay. That is the core idea behind. And let's go back and look at this example. Now we have a transmitter and now we have a receiver. Suppose they are not moving, static. The environment is truly changing, and especially this person is moving around. Okay, what we have is, let's suppose we are transmitting a signal XT, and the channel is, the propagation channel is quantified as a HT, and then at the receiver side, what we get is really the convolution of the channel and the transmitted signal, right? This HT convolves XT, right? And what we get in frequency domain is actually the channel in frequency domain, that is frequency domain received signal divided by the frequency domain transmitted signal. Okay, and the HT basically is the CSI, right? Telling you the different channel coefficients on different frequencies. Okay, and maybe this is a little bit abstractive, and let me use a more concrete example to show this point. Let's suppose we have a transmitter here and we have a receiver here. And when the transmitter is transmitting signal, and the signal starts from time 0, and it propagates through different paths, as you can see, right? It propagates through different paths and reflected by different components, and as a result, they were received at the receiver at different time. Specifically, we have 4 time beings that we receive the 4 copies of the signal, okay, reflected by through different paths. And specifically, we call this power delay profile because you're receiving the power at different delays. And we also call it impulse response of the channel. It's pretty much like when you have an impulse as an input, then what do you expect as the output, right? It's like when you have an input like pong, right? What you hear is like pong, 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 right? This is the impulse response. And that pretty much tells you how many paths we have and how far away they are from the TX to the RX, okay? And specifically, this channel impulse response is sort of associated with this CSI, that is the channel frequency response. And actually, they can be translated to each other. Okay, they are basically talking about the same thing. That is the channel itself. So the impulse response can be easily translated into the frequency response and vice versa through FFT or IFFT, right? So now we have the CSI from the Wi-Fi, and as a result, we can and we should be able to recover the power delay profile. And that tells us roughly the idea of how many paths we have and how long roughly are they, right? And now this is just a signal from one antenna. And now suppose we have multiple antennas, then as the figure shows here, one signal, when you receive it from different antennas, and you can tell that they traversed different amount of distance, specifically, right, this small delta here, and that is related to the angle of the arrival of the signal. And by looking at this small delta and comparing across different antennas, we can precisely recover the direction of the incoming signal, and that is called AOA, angle of arrival. And when you have more antennas, you can have more resolution for this angle of arrival. And suppose we are equipped with multiple antennas, and that is the case for current commodity Wi-Fi, then we are able to sort of recover the direction of the reflected signal, especially if we can extract that signal path and isolate it from other paths. We may be able to track the movement of the reflector, right, of that path. So now this is basic, right? We have the sort of spectrum analysis, and we can recover the different paths, and we have multiple antennas. We can sort of detect the arrival of the signal, the angle of arrival of the signal. Right? By combining the two information, we can actually track, right, the reflectors. Okay, and there are typically two different ways to sort of utilize such information, and we can build explicitly signal propagation model, right? We can build a wireless propagation model, and we can estimate the channel parameters like the angle of arrival, time of flight, angle of departure, Doppler effect, etc. And then they will give us signal paths and their dynamics for tracking purposes. Or we can go the other way, where we build machine learning models and we use CSI because we know that they characterize the channel on the wireless channel, and then we can map sort of CSI variations to infer different human motion, location, or activities. Right? There are two different ways of using such information. And here I want to give another example where we built a system for detecting the human hand movement. Okay, in this case, we are using commodity AP here, and we are using two pairs of antennas to detect the reflected signal from human hands, so we can allow the hand movement in the air and let the human being write in the air and recognize the handwriting. Sorry, I'm not sure if you can see the video here. And in this case, we use the reflected signal to track, okay, the motion of the hand movement, and then map that into a figure, right? It's an image, and then input it into a convolution neural network for handwriting recognition. Right? And the good thing about it is you don't have to wear anything again. This is a very lightweight way for sort of human-computer interaction, and it can be easily adapted to different human subjects, as the video suggests, even when they are having different writing styles. As long as we can accurately track their movement, we can translate that into an easy handwriting recognition problem, where we can build very mature machine learning model to recognize those handwriting. Right, so this figure shows the basic rationale of the system, where we use a Wi-Fi front end for detecting and extracting motion trajectories, and then use the machine learning model for recognizing those trajectories. Okay. Specifically, this is antennas, and about detecting the reflected signal from the moving heads. And based on that, we figure out potential candidates of moving trajectories. And then we input that into the as images to existing machine learning models and try to recognize different handwritten characters. And the particular nice feature about this system is we can easily sort of switch the handwriting applications across letters, digits, or even Chinese characters by supplying different handwriting training datasets. And we don't have to rebuild the training datasets because they have been well studied in the handwriting domain. So by simply supplying them to our system, we can get a plug and play effect, and we can accurately recognize those different input in letters, digits, or Chinese characters. Okay. Right. Having said so much about the nice features and applications of Wi-Fi sensing, right? Maybe a question that you have in your mind is, it's so magic, and is there any limit, right, in using wireless sensing? And my answer is yes, it is limited, and it's very much limited, especially by commodity devices. Okay, so there are two major diversity that we export for Wi-Fi sensing, and they are also sort of limiting the performance of our current existing Wi-Fi sensing systems. The first diversity is the frequency diversity. Okay, and this is easy to understand. Basically, when you are using a wider frequency spectrum to observe the signal, then you are getting more alpha and theta, right? If you can remember, we are getting more parameters for more frequency components, and that provides more information for us to recover the wireless channel, and that is the environment, right? If we have limited bandwidth to observing the wireless channel, then we have much lower resolution in telling the difference or dynamics of the environment. Okay, that is a fundamental limit. And in typical Wi-Fi devices, we are limited by that to 20 or maybe 40 megahertz, okay, in different frequency range. And the other limit is spatial diversity. That is a number of antennas you have, because you have to separate the antennas far away from each other so they give you independent observation of the signals. And the number of such independent observations allows you to have a better resolution in telling where the signal is coming from. Okay, and current Wi-Fi devices have limited number of antennas, and that also limits your resolution for AOA. Right. So we have been doing some research in recent years, particularly to improve the diversity with commodity Wi-Fi hardware. Okay. And that provides a general platform for all of those Wi-Fi based sensing applications. Specifically, one is for improving the frequency diversity, and that is a Splicer, which was published in MobiCom 15. The other is to increase the spatial diversity through extended antenna arrays, which is called SWAN, published in MobiCom 18. I'm not going to the details of the two works, but I will introduce rough ideas behind. So the key idea of Splicer is that, okay, while our Wi-Fi transmission is limited in a certain bandwidth, that is 20 megahertz or 40 megahertz in 5G range, but the total frequency range allocated to Wi-Fi is not limited to that. For example, in 2.4 gigahertz, we have 80 megahertz, and in 5 gigahertz, we have even 200 megahertz total bandwidth. That allows us to sort of probing the channel multiple times and then adding up the observations. Okay. Simply speaking, that is, okay, we do transmission at different frequency bands using different packets and later combine them together to get observation of a wider band. Right? The idea is very simple and looks very easy. The reality is the combination requires a lot of research and engineering efforts to remove sort of system and bias in the individual measurements. Okay. So here, let me show you some typical result when you measure a channel. Right? This is the amplitude. when you send the signal, a packet in different Wi-Fi subchannel, right? This is, we are sending in channel 1 5 times, and you can see the CSI from those packets. And this is on different subchannels. And then we move to different channel 6, 7, 8, and 9, 10, 11, 12, and 13, right? You can see that we get different CSI from different subchannels, and it seems to be pretty good, right? If we simply combine them, we're getting a bigger picture here. Not exactly matching each other, but so far, looks like pretty reasonable. We can combine them. There are some up and down, but that is fine because up and down of the amplitude is nothing but more and less attenuation, and that shouldn't affect us to recover the propagation path. And that is actually the case as well. We can combine them easily by moving different measurements up and down to combine them. Right? So far, so good for amplitude. But if you look at the phase, which is also very important because if you can remember, right, the phase basically tells you the distance information or time information of the signal propagation on different paths. Then what you end up with is like this. It looks like a total mass, right? If you focus on specific 5 measurements from the same subchannel, you can see that they're subject to certain systematic error as well as a huge random offsets as well. So how can we do with them, right? How do we combine them? And the key idea here is we first need to figure out what is the reason of those errors, right? If you look at this channel, right? What we are interested is the channel itself, that is between the antenna of the transceiver and the antenna of the receiver, right? But actually what you get, the CSI is from here, which is a channel estimator, not immediately after the antenna. Actually, the signal has to go through different modules, like the sampling ADC, that is at the receiver side, you are taking samples from the signal, and then the packet detector, that is for the receiver to detect the boundary of your packet and then extract the preambles, and then CFO, that is for moving the signal to the baseband. And after all those signal processing, you can estimate the CSI. And you can tell that, right, what you get here, the CSI, is not specifically telling you this channel, but actually this channel plus the hardware, the circuits inside the Wi-Fi. And the error comes from all those components. SFO may basically will result in a shift of your the shift of your, what is that, time shift, the phase, and the packet detector will result in the linear variation of your responses on different frequencies, and also in the CFO, right? So what you have to do is to remove all those effects from the hardware in order to get the real CSI of the channel. And that is what we did for combining the different signals. And I'm not going into the detail, but if you look at the result, with the combination successfully removing all those errors, we were able to significantly improve the sort of ranging accuracy using the CSI. Okay. This is a result that we get with only 20 megahertz observation. And finally, this is a red line is what we can get with a total combination of 200 megahertz. You can see a great improvement by improving the frequency diversity. And we incorporate this ranging technique enhanced by our splicer into a existing localization algorithm, and we can see immediately improvement that reduces the original error of like 7 to 8 meters to only 2.3 meters for a slow moving object. And if we have multiple APs, we can bring it down to even sub-meter level accuracy, right? This is how we can improve the frequency diversity. And the other work, SWAN, is for improving the spatial diversity, where we try to augment the number of antennas of existing commodity Wi-Fi. Okay. So if you look at existing Wi-Fi interface card, this is a typical Qualcomm Atheros network interface card, and this is a typical commodity AP with 2.4 gigahertz and 5 gigahertz network interface card. And they are all limited to at the most 3 different antennas. The key reason of such limit is not the antennas, but really the radio chains equipped for each antenna for decoding, ADC, for baseband process, etc., etc. Okay, so what we were considering is, okay, with a limited number of radio chains, can we extend the number of antennas? Because antennas are typically cheaper. And by that, can we obtain more diversity with a relatively lower cost? And that is a key idea of SWAN. And we try to augment commodity Wi-Fi with a microcontroller enabled antenna arrays. And we can quickly switch the radio chain to different antennas so we can get a signal from different spatial diversity. Okay, that is a key idea about it. And as you can expect, right, the key challenge is, okay, how can we do it really fast? Because Wi-Fi transmissions are in microseconds, and the protocol overhead in between different transmissions are at the order of tens of microseconds, which means we need to do really fast switch and control within tens of microseconds. And if we can achieve that, we're actually providing a low cost and plug and play solution based on COTS hardware components. And the key of the design, again, I will not go to the detail, but the key here is both on the software and the hardware. So in the software, we need to figure out a very fast communication between the Wi-Fi driver and the Ethernet driver. And then in the hardware aspect, we are going to have a very fast and reliable communication between the Ethernet port of the Wi-Fi card and an external controller, which is based on Arduino in our case, for controlling the switch of antennas. Okay. We have to make it really fast and being able to tolerate sort of resilient to errors, because we have to make sure that we switch to the right antenna for receiving the signal. Otherwise, we will be giving false estimations. Okay. And we were finally able to overcome those research and engineering challenges and come up with antenna arrays, okay, based on commodity Wi-Fi. And we were able to build phased array, which is a circular array in this case, right? And that gives us a special advantage of having 360-degree views of the signal, right? If you look at the commodity Wi-Fi with only 3 antennas, you will never be able to have a circular array having such a broad 360-degree view. And you will have ambiguity in differentiating signal from left side and the right side. Okay, but with the help of the SWAN, we were able to build a bigger array, but with very low cost, okay, for having this diversity. And our experiment shows that using the circular array, we were able to 9 antenna-based circular array. We were able to improve the angle of arrival estimation from the commodity roughly 12 degree in average to currently below 4 degree in average. Okay. That shows the spatial diversity that we were able to obtain by augmenting the antennas. Right. And most recently, we have been working on the algorithm aspect to sort of combine our measurement for both the angle of arrival and the time of flight. Right? If you can still remember, the time of flight basically is the observation of the channel frequency response, the CSI, so we can tell the length of different paths from each other, right? And then the AOA tells where this path is coming from. Okay, and conventionally, people just do them separately. Okay, using CSI from different frequencies, we can tell the different path lengths, and using the data from different antennas, we can tell the angle of arrival. And then by combining the both, we can tell where is the reflector, right, the moving object. But what we discovered in this work is, okay, instead of looking at this AOA and TOF separately, in such a case, we have the problem of resolution. Okay, for example, if you look at SWAN and S3 in angle of arrival, then they are pretty much close to each other. If you don't have enough bandwidth, then you may end up with inadequate resolution to separate the 2 paths. Or if you look at S1 and S2 in time of flight, if you don't have enough bandwidth, then you are not able to tell them either. Right? But if you combine the view, you estimate them jointly, okay, together, then you were able to accurately separate all of those passes. And if we generalize this case to having more components in estimation. For example, in this case, we are estimating the angle of arrival, time of flight, and the Doppler effect at the same time. Then we are able to tell ACE4 from ACE5, okay, without having the knowledge of Doppler effect, which is not possible, even you have AOA and TOA in this case. Right? This shows that using this joint estimation process, you were able to have this super resolution, which can get you beyond the resolution provided by the hardware itself. And this is, the figure shows the basic idea of this design, but don't be scared. I'm not going to dive into the detailed math, but basically this is a matched filter with multi-dimensional estimation of all those factors at once. Okay, and that allows us to use the maximum expectation algorithm to figure out the best match for, and so we can separate the superimposed signal into the best combination of paths satisfying our observations in different dimensions. And that is the key idea. And with that, this is what we can achieve. Traditionally, using music, you can just perform it on one dimension. In this case, time of flight that tells you the distance of the path, or on the different antennas that tells you the angle of arrival, okay, but not both. And Spotify is able to perform two-dimensional music, and that gives you the combined estimation with AOA and TOA. And our results show that by combining more channel parameters, we were able to significantly improve from that to even much lower errors, okay, and higher resolution in resolving any of those different parameters. In this case, we are combining the estimation from angle of arrival, time of flight, angle of departure, and Doppler effect together. So we can get a very low error in resolving different paths. And that allows us to have more precise estimation and sensing for different moving objects. And this shows when applying this algorithm for detecting multiple sources in the environment. In this case, we have 4 different mobile paths reflected from 4 different moving objects. We can separate them with high confidence. And we can even tell sort of different effect from human movement, like the human body movement, from the hand movement, or even the finger movement, by looking at those subtle dynamics of the different channel propagation paths. Okay. And I hope that has given you a very basic picture of the recent advances in Wi-Fi sensing and the basic rationale and the key challenges and limits in those sensing systems. And I'm going to use the last perhaps 5 to 10 minutes to have an advertisement, right? I mean, there is an advertisement for our CSI tool that we have open sourced to the community. And if you are interested in this area and you want to do Wi-Fi sensing, and I think this is a tool that I want to recommend to you for easy start. Okay. So in the past years, we have open sourced specific CSI extraction tool that was built with all the Qualcomm Atheros Wi-Fi interface cards, okay, 802.11n, on different Wi-Fi network interface cards, okay. We have been doing both software and hardware integration, and we integrated our tool into the current ATH9K driver in Linux kernel. And with some open source efforts, not only from our own group, but also from the community, we were able to integrate this tool to different versions of Linux system. In the Ubuntu systems for desktop and laptop, usually operating systems, and OpenWRT for embedded APs. And specifically I think this is a contribution from the external researcher. They have extended our tool to an Inono, which is an embedded Linux system that runs on Arduino Ring. And I think there is another effort from external researcher who extended our work to a DROM operating system. So with the help from our open source tool, as well as the contribution from the community, we were able to provide very mature tool set that you can start with for different sort of applications and on different platforms. Okay. And this is a specific maintenance page for this tool. And we have 2 versions maintained. And this is a GitHub link where you can have full access to our codes for CSI extraction. So till now, the tool has been used by over 2,000 registered users. I believe the true number is much bigger than this. This is the number that we were able to trace. But I believe there are more users for this tool. And based on this tool, there have been over 30 papers published by various research groups, okay, studying Wi-Fi sensing. And if you have interest, I think this could be a very good tool that I would like to recommend for you to try out. A little bit sort of aggressive advertising is I want to compare our Atheros CSI tool with another available CSI tool, which is based on Intel 5300. And so first I have to give the full acknowledgement to this tool, which was very great. Actually, it was the only CSI tool before our Atheros CSI tool was available 2 years ago. So it's developed by David Vessero's group from U Washington. Okay, it was very good and was the only tool that was available. But now we have our CSI tool, and I compare this one with Intel 5300. I would say that we were able to achieve much higher resolution in terms of the representation of the CSI by using 10 bits versus the 8-bit resolution for Intel 5300. And in a sense, we can have a more a higher resolution for a quantization accuracy. And also we are reporting a full range of this CSI from all the 56 or 114 subcarriers from 20 or 40 megahertz channel, while Intel 5300 only reports 30 subcarriers, which is not a full CSI profile. And our tool works for most advanced Atheros network interface cards. That's a family of APs, and they are working with OpenWRT, very easy for experimenting and building prototype systems, while Intel 5300 only works for one specific Wi-Fi network interface card. And that is the main reason I'm recommending our tool. And we also did some small benchmark measurement, okay, comparing our tool with Intel 5300. So the basic setting is very simple. We are combining, we are sharing one antenna as an input of the wireless signal to both network interface card, and we are comparing the same ground truth, but different measurements from different tools. And the result is shown here. As you can see that we are giving more data points across the subcarriers, while 5300 gives only 30. So we are of higher granularity. And if you look at the precision, you can see that we are giving better precision as well. And we have a stabler estimation of the channel. Right? And if we do it multiple times, and as you can see that, we are more sensitive. Actually, you can see that different measurements are in different color, and you can see they are scaled up and down. That is because the signal scales up and down in terms of the attenuation. And we were very sensitive in capturing such attenuation, while 5300 is not that sensitive, and also it's not very stable across different measurements. And we have a better consistency, right, in terms of the measurement. And actually, in the past couple of years, we have often received complaints from some of our users saying that, okay, our tool is not very stable. In particular, compared with 5300, I think that's a sort of misunderstanding I want to clarify here as well. That's because we are using 10 digits for quantizing our signal. So as a result, we are more sensitive. And 5300 has only 8 bits. So if you benchmark them, I mean, align them to the same scale, then you will surely see 5300 as more stable. But the actual truth is we are more sensitive. And that is pretty good for you to especially detect slight movement and detecting slight environment dynamics. Okay. But in terms of the consistency across measurements, I think we are giving a better result. Okay, so I think that's pretty much of the talk today. Thank you very much for taking part in this talk. And I'd like to take the questions from you. I hope through this talk you've been gaining basic understanding about this Wi-Fi sensing, right? What is CSI, why we have CSI, how it is derived, what can we do with it, and how we can best use it, and what is the limit and how we can improve it. Okay, so thank